card case. You said that you had like formulas or whatever. I wasn't there to get that message for the first test,
So on the day of the
so I
review,
never made one.
the class before a test,
Uh-huh.
we create the formula sheet together. Yeah.
I wish we just had 7 this summer. Stars 7, 6, 9, 6.
Whoever wants to have a big
So much easier. It's so weird. I hope so.
All right, guys. So guys, I dare to say up here that this is nothing new. The only thing that will be new, truly, is some of the words we use to describe these specific graphs. So we'll see if you believe me or not. No, somebody already don't. This is going to be 5.3 and 5.4. Okay. So the reason I say it's nothing new is because when we hit a brand new function, one thing you should expect is that we're going to graph this thing. Once we graph it, and I know this is one of your favorite things to do, we're going to start transforming it, smushing it, moving it around, extending it. Yes, I know. And when it comes to trig graphs, for some reason, those are more important because they deal with, how many of you guys are musicians possibly and work with, a few of you guys? Do you have anything, oscilloscope, anything where you look at the frequency of the sound wave? And if you alter something, doesn't it compress the sound wave and it pulls it? And even if you're not a musician, somewhere you've seen this. Science fiction movie, the guy comes over, turns the dial, and the little wave gets smooshed. Oh, well, turn the energy up, doctor. You know, something's happening. The monster is doing something, whatever. So first thing we're going to do is just make a table of values to graph sine and cosine. Right? Then we're going to play with sine and cosine for a while. And then we'll talk about the other 4 trig functions. And what I said earlier about if you know sine and cosine, you know everything else, is true with basically almost anything. So that's why we're going to first focus on sine and cosine. Is that awesome? Poor little dude. So let's look at sine. And let me make this point also. Everything we've done so far has been on a unit circle, which is actually a set of coordinates that we're not used to using. It was a very specific application. It was a unit circle. We were talking about triangles and sine of angle and knowing where we were and all kind of stuff. So it was a very specific application. We weren't terribly freaked out about it. But we want to bring this back to our good old XY coordinate system. Not circular thing. Let's bring it back to an XY coordinate system. Let's take a real look at what this looks like. So somebody help me out. Making a table of values for sine. Well, let's do some negative ones too. I'll kind of start us off here. Let's just do 0 first, and then we'll do some positives, some negatives. Sine of 0 is
1, 0.
sine likes y. At 0 degrees, it is all
0.
x. So there's no y there. So this is 0. You guys with me so far?
Yep.
When it comes to cosine, that'll be 1. All right, how are we guys? Okay. All right, let me try this. Pi over 6, also known as how many degrees?
30.
30. What's the output? What's sine of 30? A half. And think about this, at 0 here, I've only moved 30 degrees away. It can't have gotten that big yet. So it's just 1/2. You with me? And you write 1/3. So what about pi over 4? 45 degrees. Yeah. So here's where we can see that pattern I was telling you about before. Remember the root 1 over 2, root 2 over 2? The next one's going to be, curving up, root 3 over 2.
Yeah.
Somebody help me out here a little bit. So that's obviously 0.5. Root 2 over 2 is 0.707 or something. I would say 0.7 is good enough for my remarkably rough graph I'm going to do. 0.8 something, yeah, 0.9, roughly. Good enough for my scale, let's just say, all right? And then the next step would take us to 90 degrees. And of course, at pi over 2, it's sine of 91, because now it's all y. So the sine is as big as it can get. So one thing I haven't said, I can't remember if I said this directly or not, but it's just cool. Sine cannot, the value of the output of sine cannot go beyond 1 or negative 1. So if on a problem like that what we just did, if you say sine theta equals 13 over 2, something is wrong. That is bigger than 1. Sine cannot be bigger than 1 or less than negative 1. Is that cool? So be careful. That's just a little check to make sure that things ended up in the right place. So far, so good. And now, of course, we start getting into the next one would be the 30 away from this. So pi over 3 plus pi over 2. Oh boy. This would be 5 pi over 6. What's the reference angle here?
Pi over 6.
Good. Otherwise known as
30.
30 degree reference angle.
So negative.
Is that the right place? No, I went too big of a step, sorry.
Kind of going backwards.
I'm one step ahead of myself. Hold on. I'm one step ahead of myself. So we want to take our pi over 6 step away from this. So I'm sort of stepping primarily by pi over 6. I wanted to throw that pi over 4 in there too. So this is pi over 6. This is 2 pi over 6. Is that cool? Which reduces to pi over 3. This is 3 pi over 6, which reduces to pi over 2. So the next one should be 4 pi over 6, which is 2 pi over 3. Cool. And what's the angle there? That's going to be 30 beyond that, so that's 120. And the reference angle, like you said, was 60. That's 60 away from 180, right? So what's the sine of 60?
Root 3 over 2.
Root 3 over 2. And notice, I mean, I really want you to see this. It starts at 0. It slowly builds up to 1. Now it's going to slowly shrink back down to 0. Then it's going to slowly build up to negative 1.
But it's negative.
Well, it's not negative yet, because sine in the second quadrant is still positive. Okay. So we might have enough to kind of get started with this thing and see if there's a pattern so we don't have to keep going and drive ourselves insane with this table. So the biggest it can be is 1, and the smallest is negative 1. So that scale is easy. Okay. So let's go out to 2 pi, just because that's where things are going to start to repeat, right? Halfway through there is pi. Halfway through there is pi over 2. And then halfway through there is pi over 4. How are we doing so far?
Good.
Okay. So you think about it, if you do the unit circle, what values of the angles did we use? From 0, pi over 6, pi over 4, pi over 3. We used basically these to break that up. So we're really just kind of laying that circle out like that. I still want to use the same values for my inputs, because we know those outputs. So at 0, this was 0. At pi over 6, which is right in here, this was 1/2, right? Pi over 4, this was 0.7. Pi over 2, it's 1. And again, it's not going to be perfect here, but you start to see something that looks familiar, hopefully, for some people. And then it just starts to go back down, and it's actually symmetric as it goes back down. It's here, here, here. Second? Yes, sine wave. Not parabolic. It's maybe roughly parabolic in some places, but not really. Not very much. And then here, it's going to be the same. If I go past this, it's going to be that same ugly looking mound that I made. It's going to be just that same thing down here, isn't it? Because again, that's the whole idea. Once I know the first quadrant, I know everything else. So here I knew these values for the first quadrant. They're repeated again here. They're going to repeat, the negatives are going to repeat here. And then it's going to go back to there. And they go on forever from there. Okay. So this is a very strange graph compared to any other thing we've ever graphed. Polynomials, they could do that kind of thing, but eventually they go off to infinity, don't they, in some way. This one kind of stays, it stays in between here. So one thing I can say is the amplitude, that's what we call the amplitude. For this specific one is 1. How do you think you could change that? If I let you change this equation somehow, how can you make the amplitude 3?
Put 3 in front of
Put a 3 there. That would triple the outputs, and they would all of a sudden the biggest output would be 3 and the smallest would be negative 3. You'll notice the amplitude is not 2, it's 1. And it only gets 1 away from the middle at any point, at most. All right, how are we doing so far? Okay, cool. The period. And this has, remember what we said about, oh, let's see, we said that, no, we haven't said it. Period really implies that this is something that repeats itself. And really, when I say the period is how long does it take for it to start repeating itself?
2 pi, 2 pi?
It takes 2 pi for it to truly start to repeat itself. So you could say, but Jeff, it's the same value there, but it's not the same situation, is it? It's going up, it's going down, it's going up. Right here, it's the same thing again. So this guy has a period of 2 pi. Cool. All right. So those obviously become very important when we start messing with this thing. Yeah. What do you think is going to be different, possibly, with cosine?
It's going to go into the
Because what's cosine at 0? 1. So let's see if we can do this without the aid of a table. So let's see, just go to
It's
2
going to
pi.
start at 1, right?
Yeah.
Instead of starting at 0?
And it starts at 1. Output. Starts at 1 as an output, whereas sine started at 0 with an output. So when I say starts, the thing doesn't really start anywhere, does it? I mean, it's infinitely long that way, infinitely long that way. But let's just say we start on the y-axis. Go from there. And where does it go from there? What is it at pi over 2? What's cosine of pi over 2? So I'm here. Careful. Pi over 2 is an extreme, right? It's all y. Cosine of x, 0. So it's going to do this, and you know, like for example, pi over 4, it's going to be that root 2 over 2. It's going to be the 0.7 thing again. Are you guys with me? So if we start moving these things, I do not want to get this specific necessarily. I want to get the highlights, the anchor points, and then start moving this thing around. Right? Okay. So you don't have to be that specific if we're going to start doing a transformation. What happens at pi? What's cosine of
It starts going up.
pi? Yeah, it's all x, and x is -1. Right, so it's another extreme for cosine. So again, now it kind of comes down here with that sort of parabolic looking thing, but not really. At 3 pi over 2, that's down here, so of course that's going to be 0, because now it's all y. And then it's going to start to build back up again. You get up to 1 by 2 pi. Of course, it goes on forever from those 2 points. Of course, I mean, if I kept going with this, it's gonna basically look just like sine, but it looks like sine that's been moved itself, isn't it? If I took this and moved it back, by how much? By 90 degrees. I love it, by pi over 2. If I just took this and moved it back by pi over 2, that would be cosine. Okay. Maybe. So how are we doing just with that? Just with the idea of sine and cosine and what they look like? They're really the same function, just one's been moved over. Exactly, they're kind of like off from each other a little bit, but offset by 90. All right, so somebody remind me. If I have a function, this is really the hardest part about this transformation, I think, personally. If I have a function, and let's say it looks like this. Okay, 0, and this is 4. What would happen? Oops. There. Think about it now.
Look at Y.
It's actually the reverse of what you think. Because remember, what would this do? What would that do to it, really? Move it over 2 to the right. So it's always, if it's in with the letter, it's always the opposite of what it looks like, right? So this looks like it should double it, so it actually probably should cut it in half. Now, it affects the x, doesn't it? How do I know that? Because it's in with the x.
So it'd go to 2.
So it actually take this triangle and make it.
Go to 2.
Because what is f of 4? 0. Right? So here, how do I get 4 in here? What x value do I actually put in there? 2. So it makes it to 0 at 2. It only takes it half as long to make it, because the first thing I do is double the input. So that's why it actually ends up shrinking, because it helps it make it through its whole thing. Do you understand how that applies to this? This guy's period would be maybe like, because there's this triangle thing going forever, is 4. Maybe it's more than that, but anyway. This would cut it down in half. So now the picture would look like that. Why couldn't I put a 4 in here? Because what would that end up asking for?
8.
Yeah, it would end up asking for f of 8, and do I have 8 to find?
Mm-hmm.
No. Do you start to... So it's always the reverse of what it looks like. And I always like to think about whatever I plug in there, the first thing I do is double it. So it's able to get through whatever it normally gets through this long, now it's only going to take it half as long to get through that. And that directly connects to this thing. What would happen to this picture if I had sine of 2x? So it normally takes it 2 pi. Now it should take it how long to get through one period? Pi. So the period now, here's a shortcut to how to figure out the period. The period is going to be 2 pi divided by whatever this coefficient is. It's going to cut it in that many. Right? If it was a 7, it's going to cut it in sevenths. If it was a 4, it cut it in fourths. If it was a 1/2, that would actually stretch it, make it 4 pi. So now this period is going to be pi. Okay. So every single point now is normally here, but now it's going to be halfway. Right? Here it's going to be, let's go all the way here. That's going to be here. Right? So this is going to be there. 3 pi over 4. Right? Half of this. This is going to be there. See how little it sucks. So now it's going to be like this. So that smushes it. And I like that. This is a nice visual because it's like a spring almost. You're compressing that spring. So if it was a fraction in here, what would that do? That would elongate that spring, right? Cool. So anybody who's taken physics, you kind of sometimes you just go that way in your thought process. So what about? Of course, they just took it away. That sucks. So what would this be here? What's the period of this one?
1.
So remember, what's the shortcut for period? It's 2 pi, what it normally is, divided by that coefficient. 8 pi, cool. Because that's the normal period. If the coefficient was 1, it shouldn't change at all. It would be 2 pi. 2 pi over 1, just 2 pi. This is kind of a shortcut to apply that guy's transformation. Yeah. Always. When you're doing the period for cosine and sine, other trig functions might have a different period, but we've only talked about cosine and sine so far, so that's all we can say, but it will be 2 pi for those, always.
Does that change when it's not a unit circle?
Sine and cosine always reduce down to the unit circle. Always. Cool. And that's what I was saying earlier to, I think to Michaela, I don't know if other people heard it, but that's why sine goes like y, but why is it y over h? So that if it's not the unit circle, it can reduce back down. Divide by whatever h is, it's going to reduce it back down to 1. It reduces it back down to the unit circle. Cool. So if the period's 8 pi, and starting at 0, of course at 0 it's the cosine, what is it at 0? What's cosine at 0?
1.
1. And how far I gotta go up now to 8 pi. So now this is what I do normally with these things. I cut it down to my 4 major points. Halfway through, and then a quarter of the way through. Good job. And now just on top of this, you lay down what the cosine looks like. 1/4 of the way through, it wants to be at 0. Half of the way through, it wants to be at -1. 3/4 there, and then the rest it wants to be at there. That's the most ugly cosine function, but all. Which obviously does not have to be any prettier than that, really. You guys get the idea, semi-idea? I mean, this is not, the reason why I said not new is because it's not new. We've done transformations of functions before. It's just that the function itself is relatively new. So it shouldn't be that big of a leap to realize what would happen, for example, here. Let me make this a little more interesting. So what's happening? What's the amplitude here?
3 is negative.
3, good. Don't worry about the negative. It's 3. The negative is actually just going to take my regular sine function and make it do like that, right? You guys with me?
Yeah.
It's going to take all the values, what they used to be the outputs, and make it the, here it is, the reverse. I got this thing on. What's the period? Is normally 2 pi.
6 pi? Wait, I'm failing.
Yeah, 2/3 pi. So now it's going to complete an entire period inside of 2/3 pi. Okay, cool. So now, again, I'm showing you exactly the way that I kind of do this thing. Good job, Jim. Put that 2 pi over 3. And the only reason one thing we haven't done yet is we haven't moved it up and down, and that's easy enough. Or moved it left and right. And of course that would affect that value here, right? I'm starting at 0, so I'm going to end at 2 pi over 3. Oh yeah, thank you. So what's halfway through here? What's half of 2 pi over here? Pi over 3. And then half of that?
Pi over 6.
So pi over 6, 2 pi over 6, 3 pi over 6, so there's pi over 2. Could you guys set that up? It isn't horribly evil to set that up, right?
No.
It's a little bit harder when I start moving it left and right. But so far I'm starting at 0, so that's not too bad. It's a sine, so I know what it basically looks like. Normally sine starts off here, and it still is going to start off at 0, right? But now it's going to go down now. Cool. down to -3 by this point, back up to 0 by that point. Here it's going to be at 3, and then here it's going to be back to 0. How can you check yourself?
Graph calculator.
I like the graphing calculator. But what's wrong with the graphing calculator? It's not going to give you this scale, is it?
No.
If it does, that's neat. But let's plug in a point, pi over 2. If I plug in pi over 2, what's the sine of 3 pi over 2? I'm at the y-axis this way. What's the sine of 3 pi over 2? Sine likes y, so if I am
3.
here, that's -1 times -3 is 3. So I'm in the right place.
Yes.
Of course, you guys could just plug it in the calculator, but hey. Always double check, pick a point or two, just to make sure that it ended up in the right place. So let me kind of show you one complete thing with all the transformations in it. We'll do it together. So let's start to write down what's happening. And I'm going to give you a nice little thing. The book actually agrees with me on this. I like it. A nice little way to figure out where you start and where you end. So first off, let's start with the amplitude. What's that going to be?
1/2.
And the period. One little thing you have to be careful about. This is not really going to affect me here necessarily, but you need to have that number directly coming off the x. So let me say that again. If I have like square root of x minus 1, that's going to move it right 1. If I had square root of 2x minus 1, I actually have to do this to really see what it's doing. So it's going to move it right 1/2 after I apply this. So we normally apply this first, this period changing. So I have to take that 4 out to see what really is happening directly to the x. Because this minus pi is happening to 4x. So what's happening directly to the x? Take a 4 out, what do you get? Cool. So then I know, and again, this is what I said, this is basically old stuff. It's just the words that we use are different. So here the period is, the old period is 2 pi divided by the coefficient there, 4. So the period now is pi over 2. It'll get done a lot faster, right? And here's the word that we use for this shift. We call it a phase shift. Oh yes, makes it sound science fiction-y. Possibly. So the phase shift is going to be, just tell me, which way how far does it go, which way? Yeah, right, pi over 4. And then finally we have, at the very end, we're going to move the whole thing up 2. That's the last thing we do. I know. Alright, so here's my one little tip that I'll give you about. This one's got that extra piece in it that I said was going to make it harder. If it starts at 0, it's easy. You just go out to whatever the period is, and then you just break that up. I'm not starting at 0 here, am I?
No.
Because they've been shifted over by pi over 4. And tell me this. Let me double check. On page 392, I want to see if you guys actually have this, or if it's just in mine. No, you should have this. On page 392, do you see the blue writing on the side of the page? Or is it just some meds that I need to take? The only one that sees blue writing.
So,
See, here's another way to find.
yeah.
Okay. 392. So page 392, they describe this method in blue on the side. I kind of like this method. It's the way I was taught. In this book, it's a little side note, but we'll see. What you do is you take, normally if it's cosine x, it goes from 0 to 2 pi, right? Yeah, Jeff, what? So what I do for cosine of 4x minus pi is I say 4x minus pi equals 0, 4x minus pi equals 2 pi. And I solve that. And it's going to tell me where this one starts and where it ends. So where's that image that normally looks like this? Where does it actually go? And I can figure that out, but this just makes it a little bit quicker to get to it. Right? So there's other ways to do this, but I kind of like doing it this way. What do you get when you solve this for x? It's pi over 4, which makes sense because we normally start at 0 and we shift it over pi over 4. And what happens here when I solve this for x? 3 pi over. And sure enough, how far apart are these two? 2 pi over 4, which is pi over 2, which is our period. Do you see the connection? So it's been shifted. It's still better get through the whole picture in pi over 2's worth because that's the period. So if it starts at pi over 4, it better end pi over 2 later, and it does. Now when I say end, it doesn't end. It's just that's when it gets through the whole image. Cool. All right. So now, the amplitude was 1/2. The period is pi over 2, but we'll see it. Let me do this first. Make my 3 pi over 4. Then my pi over 4 is roughly a third of the way over this way. Now in here, I want to break this up into 4 parts. So if my period is pi over 2, I want to take steps of pi over 8. I don't know if you guys can move fast again. So this has got to be pi. This is pi over 2's worth. And I want to break it up into 4 parts. Why do I want to do it that way? Because then I know, and of course I've already drawn the pictures. I know those 4 basic things here. Cosine is basically this. I can do it very quickly. Bam. As long as you get those 4 pieces, I know where it's supposed to be. Right? So I want to break this part up into 4 pieces. That same way. If that's pi over 2 and I want to break it up into 4 pieces, I got to step by 8. Pi over 8. So this is 2 pi over 8, 3 pi over 8, 4 pi over 8, 5 pi over 8, 6 pi over 8, which is 3 pi over 4, which is thank God. It tells me I'm on the right track.
But when you get the pi over 2?
Period. Pi over 2. The period is pi over 2, which is because of this 4 in there, it's going to actually compress it, which makes it get through the whole thing quicker, right? If you're a musician, if you see this, that's going to be a very high frequency sound, right? If you see this, oh, right, it's like a whale. If you're not a musician, it's still true. You might not see it. So what's going to happen now? Now I want to draw this picture in there, and now that I've got the 1/2 set up, it's going to be, it's not flipped, it's positive, right? So where does it start here? The first thing is going to start at the max, because I know what the cosine looks like, right? It's going to go to 0, it's going to go down here, go back to 0, then it's back up here. It's always got this shape to it, and then it goes forever on after that. So this really feels like all the other functions we've ever done. If you know the shape of it, you can put a few points and then just put the shape in. If you don't know the shape, you need a hell of a lot more points to to get it. I know the shape of the cosine. If I could just set up where I want to put that one representative image, I then put that one representative image, I'm done. Yeah. Yeah, so now the last thing, again, the last thing you do, up by 2. So make sure everybody's cool with me up to this point. Any shifts up or down, you just do it at the end. Too much crap to keep track of there. This was enough. Now the last thing you do, up by 2. I didn't even give myself enough room. That's 1, 2. So it's got to go 1, 2. My scale is too big for this. All right. Let's say this is 1, 2. There we go. So now the maximum is going to be 2.5. What's the minimum going to be? 1.5, right? So then it still has an amplitude of 1/2 there, doesn't it? So I can, if you can be here and here. So now I just move everything up to be in between those two. So this goes right up here. This goes right up here. This goes, this one goes right here. So everything just goes up 2. Not a big step here. And then finally there. So that's why that's the last thing you do is just shift it up or down. Because this is hard enough to get without doing that at the same time. That's crazy.
What shifted?
Say again?
Which number you shifted? Or like 2? Oh, the 2? Oh,
Yeah, cool. So let me ask you this. I'm not going to make you draw one right now. Just tell me everything you can. You don't have to graph it. Tell me, don't tell me, but write it down. Everything you can about this graph.
Is that -8?
Yeah. So tell me the basics, tell me the amplitude, the period, tell me the phase shift, and then tell me where would it start, where would it end?
I got a question about
Oh, yeah.
oh no, find period. What I it was between 0 and 5. That's what it was.
Oh, yeah, you can do that.
0.
Yeah.
You know what I mean?
So you have 0 less than or equal to this.
Yeah, that. That works too, right?
Which is basically what I'm doing. I just break it up into 2 parts. But this is the same thing. You're right. That's cool. So what I did was I made this equal 0 and this equal to 5. And when you do the same thing, but you just make it look more like it's contained you. Make sure everybody started right. What's the very first thing you should do within here? Yeah, take out 3. Taking a 3 out is the same thing as dividing by 3. So you end up with pi over 6. So what's the amplitude?
8.
8. That's the easiest question there is. What's the period?
2 pi over 3.
Beautiful. 2 pi over 3. What's the phase shift?
Pi over 6.
Pi over 6.
Right.
Here. And you can either do that inequality or the start and end. If you take 3x minus pi over 2 equal to 0, and 3x minus pi over 2 equal to 2 pi, you can figure out where it should start and end. And really, I really desperately want you to understand, this goes forever, of course. This goes forever. When I say start and end, it's just so I can draw that representative piece of it somewhere easiest. That's what this really does for me. So here I get x equals pi over 6. Here I get x equals 5 pi over 6. Yeah. Is my period correct? These are 4 pi over 6 apart, which is 2 pi over 3, so a period is in between those two. Cool. And then, of course, one last thing you can tell me. Oh, boy. Sweet. Okay. So homework's kind of nice. It doesn't have a ton of these. It kind of builds you up to it.
Yay.
And it gives you a couple like this.
So, interesting.
So last couple things, and I'll let you guys out of here a little early. Now these things are going to be strange, because they all involve functions in the denominator, don't they? They're all defined. So anywhere that these original functions go to 0 are places that those functions have to go to infinity or negative infinity, right? Okay, semi with it. I mean, that's not a specific statement at all. It's just like it's going to have to happen somewhere. So for example, if I take sine, and I know that, let's just do a couple of quick things. And then I'll show you a nice visual that will make graphing these things easier. Sine of 0 is 0. Sine of pi over 4 is sine of pi over 4 is root 2 over 2. Yeah, the 45-degree ones are the nice ones. Both sine and cosine are root 2 over 2. You almost can't go wrong, except for maybe negative. Pi over 2 is sine of pi over 2. 1. I skipped 1 in there. Be careful. Just because I mean, sine of pi. Good. 0 because it's all x. So there's no y, so sine is dead. Sine of 2 pi again. 0. So if I look at cosecant, what's the cosecant of 0 then? Considering that cosecant is defined to be 1 over sine. Yeah, so this will be undefined here. This will be, remember this was 1 over radical 2 before we rationalized it, so root 2. This will be 1, and it'll be undefined there and undefined there. Is that cool? And that's not a big step to take. If you're good here, you're certainly good here. It's just turning all these upside down. Yeah. This. So the nice thing is, visually, I should give myself a little more room here. And what else makes it? Cosine and sine, they both can't go beyond negative 1 and 1. Secant and cosecant, therefore, cannot go within negative 1, if you think about it. They match up at 1. Sine is always less than that away from there, so cosecant is going to have to always be bigger than that away from there. So they actually start at 1 and go up, or down if I'm down there. It's very neat. They look a lot more parabolic. So here's the sine function. You can do it. There's my sine function. So a cosecant would be at 0 and at pi, it's got to go to infinity. So there's a like asymptotes here. So my cosecant is going to come in just like that. This is an asymptote here. You guys see that? So at pi over 2, they match. They're both at 1. Away from pi over 2, sine gets smaller, so cosecant must get bigger. Because I'm dividing 1 by a number smaller than 1. I'm going to get bigger, bigger. And of course, as these approach 0, those are going to approach infinity. So not surprisingly, it's the same picture, just down here, up here, down here, up here, down here, up here, forever in both directions. Everywhere this has a hump down, this guy is going to come in like that. They match up there, they match up there. I'm hopeful. So the biggest sine can be is 1, so the smallest cosecant can be is 1. Vice versa for the negative values, right? Now, so what should secant look like? Same thing, just shifted. So it'll sit on top and below cosine. It'll have its own little parabolic looking things. These aren't parabolic, but they look like it. So cosecant looks the same thing, but it just picks this up and moves it back a little bit, so now it's not cosecant, secant. So then it looks more like it's coming off of a cosine. Same image. So I'm hoping. Nothing major there, to tell you honestly. The last one then, the one that's not like any of that, is tangent. If you think about tangent, tangent is sine over cosine. So where is it going to have problems? Where will it be undefined? Yeah, when cosine is 0. And when is cosine 0? Like cosine is 0 at pi over 2, 3 pi over 2, negative pi over 2. All these multiples of pi over 2, right? Kind of with me? So here's a way to concisely write that. Let me see if you guys like this. Why can't I do like n pi over 2 to represent these? N pi over 2, like negative and positive natural multiples of this. Couldn't I get 2 pi over 2? Is it 0 at pi? No. So there's a better way to write this. It's pi over 2 plus some multiple of pi. So what's pi over 2 plus pi? 3 pi over 2. What's pi over 2 minus pi? Negative pi over 2. So this would actually capture all the places where tangent is going to be undefined. Okay, so the basic idea is wherever cosine is 0, tangent's going to be undefined. So tangent's going to have how many vertical asymptotes? Infinitely many, of course. So let's see what else happens here. So let's try to draw one representative picture, and then it's going to repeat itself over and over again. So at 0, what's the tangent? What's the tangent of 0? 0. Hello. So at 0, it's 0. Now where's the first trouble spot? Pi over 2. So let's go halfway to that. Pi over 4. What's the tangent of pi over 4? Remember, pi over 4 is where sine and cosine are the same. So what's the tangent then? 1. So at pi over 4, it's 1. What about at negative pi over 4? Yeah, because now what quadrant am I in for negative pi over 4? Fourth quadrant. And that's where x is positive, y is negative, so it's got to be a negative tangent. Cool. Now, before you think this is a straight line, it's going to have a problem at pi over 2 and negative pi over 2. That's where the vertical asymptotes are that it hits. Or just two of them, anyway. So this is kind of cool. Exactly. Cosecant and secant happen to have a piece that looks parabolic. It isn't, but what the hell? It looks close enough. It's a nice way to remember how they look. Tangent and cotangent are going to have parts that look cubish. Because it's got to go through here, and then it's got to kind of slam up against there. So it's going to look cubish. That's a really horrible picture. So what's it going to do? It's going to repeat this same image over and over and over. Can somebody tell me? We didn't do a study of this. Let's do it backwards. We've drawn the picture. What's the period? Not amplitude. Period is truly how far is it from this side to that side? Pi. So cosine, sine, therefore secant and cosecant all have the period of 2 pi. Tangent and cotangent have a period of pi. Bless you. With me. So if I, we're not going to do a lot of this kind of thing, but if I did have this, what would this guy's period be? What is it normally? Pi. Divided by the coefficient, now it'll be pi over 4. Same process, you just have to use pi instead of 2 pi. Because tangent is pi normally. Okay. So now we'll do the same picture over and over and over forever. What would cotangent look like? Yep, good. So it's, I think, I don't know if they summarize everything. Not really. But they sprinkle it through section 5.4. They have cotangent, tangent, cosecant, and secant images. All right. So I think that's plenty. Quiz on Monday? If you want one. No. I was thinking about making it Wednesday because I think a few of us are still trying to catch up with the homework.
Yep.
You desperately, I would highly suggest you leave that and get into 5 and 6 immediately. We haven't done so yet. So we'll have a quiz on Wednesday.
What section did we go over today?
5, 3, 5, 4.